Welcome back. Before we get started, I'd like to revise something that I said in the very first lecture. I said that this should be roughly a 16-hour lecture series, but after the first two lectures, I've noticed that I'm actually going slightly slower than I do when I lecture live, so the lecture series might go a little bit longer than 16 hours, but don't worry if you're taking the course for credit. The last few lectures are non-examinable anyway, so you're probably not going to go beyond 16 hours of examinable material in any case. Okay, so where we left off last time was with three questions that we wanted to answer in this lecture. The first is, why should we have zero curl of the superfluid velocity field? And we argued sort of phenomenologically why this might be a reasonable thing for a zero dissipationless, for a zero viscosity dissipationless fluid, but we didn't really derive it in any sense, and we're going to try to do a little bit more of that derivation in this lecture. We'd also like to know, why is it that this superfluid, why does it superflow? Why does it flow in the viscosity? It's not implied by the condition of no curl, and I'll explain why that is, and we'll try to derive what the condition is for having something with zero dissipation, something that will superflow. And the third thing we'd like to derive is, what is the superfluid density and the normal fluid density as a function of temperature. The sum of the two is just the total density, but we'd like to know what each one is as a function of temperature. The only thing we know right now in our two-fluid model is that the sum of the two should be the total density. Okay, so those are the three questions. If we had a fourth question, we'd have Passover Seder. Appropriate because this week is Passover. But we only have three questions, so it's not a Seder. So we have three questions, and the first one we want to start with is, why is the curl of the velocity field zero? So in order to do this, we need to start with a little bit more microscopic picture of what our superfluid really is. And we think about it in terms of the phase transition coming down from high temperature through the superfluid transition into the superfluid phase. And the thing that describes phase transition is what's known as an order parameter. And the order parameter in this case is going to be something we'll call psi of r, which is going to be very similar to a wave function. It's a complex valued object. It plays the role of a wave function in some sense. If we're thinking about a Bose-Einstein condensate, then this, except for normalization, then the order parameter is strictly just the wave function of the macroscopically occupied eigenstate. That's it. So it's very, very useful to think in terms of the Bose-Einstein condensate in order to get some intuition for what this order parameter is doing. Now, if you've studied theory of phase transitions or Ginzburg-Landau theory, you've already seen what an order parameter is. If you haven't studied those things, well, hopefully someday you will, but it's not really crucial. The idea of an order parameter is that it describes the phase you're in, and it describes it in terms of what symmetry has been broken as you go into the phase. So in this case, what symmetry has been broken as we went into the superfluid phase? It's actually a gauge symmetry. Why is a gauge symmetry broken? Well, we can have a wave function describing a particular eigenstate, the lowest energy eigenstate, but once we write down that wave function, you have to choose a gauge for it. You have to choose a complex phase for that wave function. You can write down the wave function. It might be a constant if you're in a very large system. It might be a sort of a sine wave or a cosine if you're in a particle in a box kind of thing. The lowest energy eigenstate of a particle in a box is sort of a cosine wave or something. But you have to assign it an overall complex phase, a p-factor, e to the I theta. And it doesn't matter what that phase is, but you have to choose one. And that's the symmetry that's been broken when you go into this phase. So this object psi is going to be oops, I just erased it. Don't want to do that. Bring it back. This psi is going to be the order parameter describing the phase. Think of it as the wave function of the lowest occupied eigenstate for VEC, except we're going to change the normalization. We're going to normalize it we're going to normalize it such that it goes to 0 at the phase transition. So above the phase transition, the order parameter is 0. You don't have any superfluid. When you go through the phase transition, the wave function continuously increases from 0. Okay. All right. Now that's great for a Bose-Einstein condensate. You can actually just talk about the wave function of the lowest macroscopically of the lowest eigenstate, lowest energy eigenstate, which becomes macroscopically occupied below the critical temperature. But what do we use for a superfluid where we have interactions? Well, for a superfluid, our psi of r is going to be the expectation of the annihilation operator at position r. So psi hat here is the operator that removes a boson from the system. And that may seem a little bit mysteriously right now, particularly if you haven't played around with particle annihilation operators before. But we're going to come back to it in the next lecture and work with this in a little bit more detail. But what I want to take away from it now is that we can define an analogous wave function for the condensate even in an interacting superfluid, not just in a non-interacting BEC. But whether we're considering an interacting BEC or an interacting superfluid or a non-interacting BEC, we want to normalize the order parameter slightly differently from the way we usually normalize wave functions. We want to set the integral over all of space of the order parameter squared to be the total number of superfluid particles, superfluid particles. For the BEC, that would just be the number of particles in the lowest energy eigenstate, whereas for the superfluid, it's the superfluid fraction, the fraction of particles that are in the superfluid part instead of the normal part times the total number in the system. So this is a macroscopic number, capital N. Macroscopic number of particles rather than the number 1, which is how we usually normalize wave functions. And this the total number of superfluid particles goes to 0 at the critical temperature at the phase transition. So the next thing we're going to do is we're going to write the order parameter as a magnitude times a phase. Now, both this magnitude is a function of position, and the phase can be a function of position also. Now, the phase theta is defined modulo 2 pi, 2 pi only, and defined modulo 2 pi because if you change theta by 2 pi, you'd still have the same phase sitting here. Wouldn't change anything. This quantity here, up to normalization, is the wave function of the BEC. Would be, for example, EDI theta. Okay, if it's a uniform system, it would just be EDI theta over the square root of the volume. If it was just a completely uniform system that we were considering, and this part here tells you how many particles are in the condensate. So this is now a square root of a superfluid density that differs from rho s, which we saw before in the last lecture, by a factor of the mass. That was a mass density, and ns up here is a number density. Okay. All right. So the next thing we're going to do is we're going to treat the wave this order parameter psi as a wave function. Psi would treat it as a wave function. This is part of Landau's genius. He realized that this order parameter can be treated like a wave function, and then we can write a mass current density Js with the usual way we do with a wave function. We write psi star p is an operator here times psi minus p operator on psi star psi, whereas p is momentum. Since p is momentum, here, since P is momentum, P equals momentum, that means that Js is mass current density. Mass current density. And then we just do a little bit of manipulation, remembering that psi we've written as square root of ns e to the I theta. We can, and momentum operator is, I guess, minus I h bar times the gradient. We can rewrite this as Js, the mass current density, is minus I h bar over 2 psi star gradient psi minus gradient of psi star times psi, and we'll use the fact that using this equation up here, we'll write gradient of psi is gradient of the density over 2 times the density plus I gradient of theta times psi. It's just a little algebra. Taking the derivative of this square root, and the derivative upstairs brings down an I gradient of theta. And we plug this into here, and we then get the mass current density is h bar, Planck's constant, times the superfluid density times the gradient of the phase theta. Now, this mass current density is also going to be equal to the mass density, rho s, the mass density, superfluid mass density, I should say superfluid mass density. Maybe up here, this is the mass current density, it's actually the super mass current density, and this is the super density, times the velocity of the superfluid, which allows us to derive that the velocity of the superfluid is nothing more than h bar over the mass. So where did that mass come from? That came from the fact way up here that the superfluid mass density is related to the superfluid density by a factor of the mass. So that's how going from here to here, we pick up a factor of mass. Here's the factor of h bar, and then we get, of course, the gradient of phase. Okay, and so the superfluid density, so superfluid velocity here is now a gradient of a phase. You write that a little nicer. Gradient of the phase theta, which tells us immediately that the curl of the velocity is 0, which is what we wanted to derive. So that's our result, and it comes from thinking about the superfluid order parameter as if it's a wave function. So if we know this is a quantum mechanical quantity, we have a good idea that we're going to have 0 curl of the velocity. Now we can do more. We can imagine taking the integral of the velocity around any closed circuit in our sample. So we'll take a closed path in the sample. Let's call it C in the sample. Oops. Let's put it somewhere else where you can see it. Yeah, I know how to do that. Let's move that down there so you can see it. Okay. So we're going to take it around some closed circuit, whatever shape it is, and we're going to integrate the superfluid velocity dot dl around that closed circuit, and plugging in the expression for that will be h bar over m integral around that closed circuit of gradient of theta dot dl. So this circulation, so when you integrate a velocity around a loop, like we're doing here, that quantity is known as a circulation. So circulation is h bar over m times, well, what is the integral of a gradient around of theta around a loop. Well, theta has to come back to itself modulo 2 pi. So whenever you integrate let's just remind ourselves of this for a second. Maybe I'll do it. Okay, let's move this out of the way. Okay, we'll remind ourselves that if you integrate a gradient from a to b, you'll get theta at theta at b minus theta of a, theta of b minus theta of a. So when we calculate the circulation, we get the phase at the endpoint minus the phase at the initial point, and the endpoint and the initial point are the same point. So you would think that well, maybe that means you get a total of 0, but in fact the phase is only defined modulo 2 pi. So the circulation is actually h bar over m times 2 pi times an integer p. P is an element of the integers. So just to repeat that again, if you integrate a gradient along some path, you get the value of the function theta at the final point minus theta at the initial point, and here the initial point and the final point are the same, but you don't know what theta is modulo 2 pi, so you could have picked up any integer times 2 pi times the prefactor of h bar over m. So we've just derived that the circulation in a superfluid, the integral of velocity around a loop, is quantized in units of h bar over m. So h bar over m equals the unit of circulation, a quantum of circulation, quantum unit. Quantum kind of means unit, doesn't it, of circulation. Okay, so we just derived that this factor here, h bar over m times 2 pi, that's just h over m, is the, h is Planck's constant without the slash in it, is the quantum of circulation, the unit circulation. Okay. Now we can do more than that. Suppose we have a great big bucket of fluid. So fluid's everywhere here. Here's a big bucket of fluid everywhere. Lots of superfluid like this, and we take our path entirely inside that bucket of fluid. That's our path that we're going to integrate around. Then we know that our circulation, integral of v dot dl, we can use Stokes Theorem on this to calculate this circulation, and we'll get that that's the same as the integral. So this is over the boundary C. Let's call that the boundary of D. So this region here is D up here. C is the boundary of D. So the integral over the area of D times the curl of Vs of the velocity, and that's 0 because we derived that the velocity field has 0 curl. So whenever you have a path that goes around a region and the entire region is filled with fluid, there's no circulation in that around that path whatsoever. However, it's not always the case that this will be true. For example, if we have let's draw another picture here where we have that you'll have 0 circulation. So here's another picture where we have lots and lots of fluid, and let's see if I can erase a little region in the middle. So say there's a hole in the middle where there's no fluid. Like imagine that this is someone cut a hole out of the fluid in the middle. Maybe you have a toroidal region and or like a bundt cake. You know what a bundt cake is? It's one of these cakes with a hole in the middle. And if I take my path around that hole, then I'm no longer allowed to use Stokes Theorem, because the velocity is not defined in this inner region here. There's no velocity, no meaning to V, superfluid velocity in that region there, where there's no superfluid in that region in the middle. So the only thing we know in this configuration is that the circulation Vs.dl is going to be the circulation quantum circulation quantum m times some integer p. P is an element in the integers. Don't know what that integer will be, but it doesn't have to be 0. It has to be 0 only when you can fill in the entire region with fluid. Only when there's fluid and velocity is defined everywhere on the inside. Now the hole in the fluid here, where you can't define the velocity field, it doesn't need to be very big in order for this circulation to be non-zero. It can be extremely tiny. There just needs to be at least one point in somewhere in the center of that circulation loop where there's where the velocity field isn't defined. In other words, where the superfluid density drops to 0, and it can be an extremely thin tube. And this actually happens in superfluids. So you imagine a big region of superfluid. There might be just a tiny point in the center where the superfluid density actually drops to 0, and the fluid circulates around that region a finite amount. So if you think, these things are known as vortices. If you think in 3 dimensions here, this vortex is a vortex line, and the fluid circulates around that line. The phase of the order parameter wraps by some integer number times 2 pi as you go around that vortex line. And right at the position of that vortex line, the superfluid density goes to 0. In fact, in real superfluid helium, these vortex lines can be extremely small. They have a core where the superfluid density drops to 0, and that core can be on the order of an angstrom. Now, the way these vortices are quite important. They were actually predicted by Feynman, and the way you understand why they more or less have to be there, it has to be possible that you can have circulation in a bucket. So you imagine taking a bucket of superfluid helium, a big bucket of helium. You take it above the superfluid transition temperature, it's just regular helium, and you start it circulating around. You start the whole bucket rotating around. Let's see if we can draw it. So you take the bucket like this, and you start it rotating around. So everything's going around like this, and then you cool it through the superfluid transition temperature. And where's that circulation going to go? Everything's going around in circle. It can't all of a sudden vanish. The circulation doesn't vanish, but where it goes is that a whole bunch of these vortex lines nucleate through the system, and the vorticity around each vortex line might be 1 unit or maybe 2 units, but a very small number of units around each vortex line, and the total circulation around the whole bucket, V.dl, can be very, very big, much bigger than 0, much bigger than 1 unit, 1 h over m. It can be some huge number with many, but each individual vortex carries just 1 quantum. Okay, so these vortices, actually, we'll discuss later, they were actually predicted for superconductors before they were predicted by superfluids, and this is another case where Landau got things wrong. Landau prevented his student, Alexei Abrikosov, from publishing his prediction of vortices in superconductors because he thought it was wrong, and then Feynman published his prediction of vortices in superfluid helium, and then Abrikosov went back to Landau and said, hey, look, Feynman's just predicted these vortices, maybe it's all right in superconductors. And then Landau said, oh, okay, maybe it's okay, and they published it, and Abrikosov won a Nobel Prize for it many years later. Anyway, So the quantization of circulation is one of the fundamental properties of the superfluid. And it's sometimes argued that the quantization of circulation is a good argument for persistent currents. So why is that? So you have a big tube of superfluid, and you start fluid flowing around the tubes. So it has some large circulation. It's going to be quantized to circulation. It will be h over m times p. It will be the circulation. Integral of v dot dl is be some quantized integer. And the fact that this is an integer, you might think that will prevent it from, it locks it in and it prevents it from changing continuously. So if there's some activation barrier to that integer changing to the next lowest integer, you might think, well, maybe it can't, it gets stuck and can't move at all. If this thing, say the circulation is 5 units or something, there may be an activation barrier for this to drop down to 4 units. So you might think, well, that explains why it is that the fluid never stops flowing, because it can't get over the activation barrier to drop the circulation down 1 unit. And often you'll even see this in books, that the quantization of a circulation explains the dissipationless flow of a superfluid. And it's not true. It's incorrect. So the reason it's incorrect is while the circulation may be stuck at, say, 5 units of circulation, that doesn't guarantee you that that you're not dissipating energy. You can dissipate energy by creating low energy excitations, and those low energy excitations will have the effect of heating up the system and reducing the superfluid fraction. And even though the circulation is fixed, remember the circulation is an integral of the superfluid velocity. So the superfluid velocity stays fixed. It doesn't guarantee you that the superfluid density doesn't start dropping. And if the superfluid density starts dropping, eventually the superfluid density, you could heat it up enough that the superfluid density drops all the way to 0. So this actually does happen. And this is the kind of thing that prevents a non-interacting BEC from actually having superflow. That it's not that the circulation changes, it's that the superfluid fraction drops and the thing heats up and dissipates energy and eventually goes above the superfluid transition, and you lose the superflow. Okay, so this Landau understood immediately. So we then move on to our second question, which is, what then if quantization of circulation isn't what causes superflow? What is the criterion for superflow? This brings us to the Landau criterion for superflow, one of Landau's beautiful arguments. And the way this, actually getting this argument right is nothing more than understanding Galilean invariance correctly, more or less. So it's one of these arguments that it's surprisingly simple, but also surprisingly subtle. So what we're going to do is we're going to imagine that there is an excitation spectrum for the fluid. We'll call it E of P, and this will be an excitation spectrum measured in the rest frame of the fluid, in rest frame of fluid. So the momentum is measured in the rest frame of the fluid. The energy is measured in the rest frame of the fluid. Now, once we decide that there's some excitation spectrum, we are going to imagine taking that fluid and flowing it past a wall. Okay, here's a wall like this, and we're going to take the fluid and we're going to flow the fluid past the wall. Okay, like this. And we want to know, does that fluid make excitations? Because if excitations are created in that fluid, then it's dissipating energy and you don't have superflow. Okay? So the question is going to boil down to, is energy momentum conservation going to allow for for creation of these excitations. We can think of these excitations as usually called quasi-particle excitations. So in order to figure out whether excitations can be made, we want to shift back to the frame of the lab. Okay, we want to think in the frame of the lab and ask what is the excitation spectrum in the frame of the lab. Well, okay, we know the excitation spectrum in the rest frame of the fluid, but in the frame of the lab, we need to write like this: E in the lab frame, E in the lab frame. So this is E in the rest frame, or the fluid frame. Let's call this the fluid frame up here. Fluid. We want to know what the energy measured in the lab frame is. Okay, energy in the lab frame of P. So P is still measured in the rest frame of the fluid, but any energy in the lab frame is going to be energy in the fluid frame of P minus V dot P. So this is my claim of how it is that the energy changes when you go from one frame to the other. And it's actually, it might look kind of natural, but let me try to make it more obvious why it is that that this is how the energies should transform when you go from one frame to another. You know that when you have a particle in quantum mechanics with an energy epsilon, that means there's some wave function which is whose phase is precessing at e to the minus I epsilon t over h bar. Okay, that's e to the I minus I h t. Okay, now if this let's think of the wave function of this particle with momentum p in the fluid frame. That's e to the I. Let's call it p dot x. I guess over h bar is the usual plane wave with of something with momentum p, and then we'll write minus I energy t over h bar as well here. Okay, so this is all in the fluid frame. Okay, this is how a particle, a wave with momentum p and energy epsilon would look in the fluid frame. Okay, now let's shift to the lab frame of p, and what changes? Well, we can write this as e to the I p dot. This will now be I guess x plus vt, right? Because the position is moving in the lab frame, minus I epsilon lab t over h bar, and we can just move this. Oops, sorry. This is E fluid. This is E fluid. We can just move this PVT over to here, so this becomes e to the I. There's our own h bar here. E to the I p dot x over h bar e to the minus I energy fluid minus I guess plus minus I. Sorry, minus p. There's no I there. Minus p dot v here times t over h bar. So I'm just moving this vt term into over here, and then this will be the new energy in the lab frame. Okay. So another way of thinking about this is that it's really just the Doppler shift of the energy when you go from one frame to the other. So we're really looking at a Doppler shift of a frequency. The energy, in quantum mechanics, energy is a frequency. So we're seeing the Doppler shift of that frequency, as we're changing the position here, x plus vt, that vt gets moved over here to become a shift in the energy. So, at any rate, the energy in the lab frame of P is going to be the energy in the fluid frame of P minus V dot P, where V is the velocity of the fluid with respect to the wall. with respect to the lab frame. So this is lab over here, lab, and this is fluid over here. Okay, good. So here's the whole point of the argument. If the energy is in the lab frame, if E lab is less than 0, then excitations are created. Then you make excitations and dissipate. And if E lab is always greater than 0, if E lab is always greater than 0 always, then no excitations. And if you can't make any excitations, you can't dissipate energy, and you get superflow. Okay? So, what is the condition then for E lab to always be greater than 0? Well, we think for a second about this dot product. The largest this dot product can be is if P and V are in the same, pointing the same direction. So we'll consider that as the limiting case. And so we'll take P parallel to V. That's when you're most likely to have the lowest energy in the lab. You get the lowest energy in the lab frame if P and V are pointing in the same direction. So if E, this is in the fluid frame, if E fluid P over P is less than the velocity, then excitations are created. That means the energy in the lab frame will be less than 0 for certain excitations P created. And if this is not the case, then excitations will not be created, and you have superflow. So let me draw a diagram, or maybe we'll derive first the critical velocity. We'll write critical velocity is then the minimum over all P of energy P over P, where this is E is lab frame. It's in fluid frame. So let's draw a fluid frame there. So let's draw a excitation spectrum like this, like this. So this is the momentum, and this is the energy of momentum. And let's just draw some particular excitation spectrum, which you might have, something that looks like this. There will be some velocity like this. Oops, try to get it to be tangent to that curve. Okay, it's supposed to be tangent right here. That's supposed to be tangent there. This is the critical velocity. Critical velocity is that slope there, that it is the minimum of E of P over P. If you go to any higher velocity, then you'll intersect this excitation curve, and those excitations will be created in the lab frame, and you'll dissipate energy. And if you're at velocities that are lower than this, then you never create any excitations. Okay, so let's look at a couple examples. So a simple example is a non-interacting BEC. Non-int BEC. So in this case, we know what the excitation spectrum is. For a non-interacting BEC, the excitations are just taking a particle out of the condensate and making its excitation to some other excited eigenstate. So its energy as a function of P is going to be P squared over 2m. So the critical velocity is, remember, it's the minimum over P of E of P over P. So that's minimum over P of P squared over 2m. P squared over 2m divided by P. And this thing is, well, okay, it's going to be 0, because you'll have P over P, and the minimum of that is when P equals 0. That goes to 0. So a non-interacting BEC has 0 critical velocity. At any flow rate, you will create excitations at small momentum, and you'll dissipate energy. On the other hand, you may or may not know this fact, but we'll derive it later on. If you took Sid Parameswaran's course this last fall, you'll have actually done this calculation. We'll actually do it maybe next lecture or the lecture after. For a Bose gas, weakly interacting Bose gas interacting, weak interactions with a weak ints, where the interaction is, some sort of delta function times u times delta function of Ri minus Rj, something like sum over I less than j, call it I less than j, I less than j. So this is the interaction term of the Hamiltonian, some delta function. So the bosons interact when they hit on top of each other with a delta function of amplitude u. So we calculate the excitation spectrum of this E of p. And we'll actually, I think we do this also as a homework exercise, and we'll do it in lecture, and it's also was part of Sid's course as well. This is the exact expression, p squared over 2m plus density times u squared minus density times u squared, and that we can rewrite as p over square root of 2m. I'm just going through this really quickly, times 2 density times u plus p squared over 2m. And if we try to find E of p over p, so E of p over p, this will be 1 over square root of 2m, and I guess we'll have, again, the factor of 2n u plus p squared over 2m, and the minimum of this over p, so min over p, is just going to give me, the square roots of 2 are going to cancel, and I'm going to get square root of nu over m, maybe plus some small corrections. No, actually, if we're looking for the minimum, that's actually going to be the exact result. And this is actually going to be the critical velocity, which is also the sound velocity in this case. So we're going to have a critical velocity, v crit, which is greater than 0 for the interacting BEC. Now, I guess I should do a little bit of truth in advertising before leaving this subject. And the little bit of truth in advertising is that attempts to measure the actual quasi-particle excitation spectrum and compare it against the critical velocity actually don't really agree very well with this Landau criterion. Typically, the Landau criterion for superflow is much too generous, that the actual critical velocity is much lower than Landau predicts, and it actually, in addition, it depends on the geometry of the experiment. And the reason for this is believed to be that in Landau's calculation of the critical velocity, he did not consider the possibility that by creating a superfluid flow, you can spontaneously create vortices. And the spontaneous production of vortices gives another way to dissipate energy, and so at actually a somewhat lower velocity than the Landau critical velocity. So it's a beautiful argument. It has a lot of truth to it, but there's a more complicated physics associated with creation of vortices. Okay, so why do we still teach this? Well, we still teach this because the same argument can be used for something else, which is actually does come out right and is rather beautiful, but it sort of gives you a warm up for this other calculation. So Landau went further with this type of calculation to our third question. So our third question, remember, is question 3 was what is the normal fluid density as a function of temperature, and the superfluid density as a function of temperature is just the total density minus the normal fluid density. So this is the when I write it as rho, it's the mass density. So Landau made a prediction. We'll go through the prediction in a moment. And then he went and he tried to get an experimentalist to do the experiment. He even explained to the experimentalist how to do the experiment. The experiment is quite beautiful itself. So the way what he's going to try to do is to try to measure what the normal fluid density is, and the way he does it is, or the way he wanted to do it, is you take a bucket of your fluid, like this. Here's your superfluid, like that, and you hang in the bucket by a wire a disc like this, stacked on another disc, like this, until you have this stack of very, very closely spaced discs with very, very thin slots in between them. Okay, they're supposed to be vertical, like that. And then this thin wire here is going to act as a torsion oscillator. It's going to rotate back and forth. And using that, the torsion oscillator is going to measure the moment of inertia of this stack of disks. Now, the point of this experiment is that with regular fluids, and including the normal fluid fraction in a superfluid, the fluid gets in between the disks and sticks to the walls of the disks. And then when the stack of disks rotates, the fluid rotates with it. The fluid that's stuck in between between the layers of the disks, because of its viscosity, rotates with the disk and contributes to the moment of inertia of that stack. However, superfluid has no viscosity and doesn't stick to the disks, and it just flows right past the disks. So the point would be that this experiment would measure only the normal fluid fraction. So inertia, write this, inertia of stack of disks. Measures the normal fluid density, but not the superfluid density. Okay, it's a beautiful experiment, and he needed to find someone to do the experiment, and he found a young and eager scientist by the name of, and I love this name because I think it's one of the best names in all of science, Alefter Andronikashvili. Now, let me say a couple words about Alefter Andronikashvili. This became known as the Andronikashvili experiment. So whenever you see a name that ends in Vili, you know it's from Georgia. Then it was the Soviet region of Georgia. Now it's its own country. And Vili actually means, I believe, in that language, it means descended from. So Alefter was descended from the Emperor Andronikash of the Eastern Roman Empire in, I believe, the 12th century. Andronikash himself was not a very nice guy. He slaughtered lots of people, and then he met a very bad end himself. But anyway, Andronikashvili was, in some sense, he was considered part of a royal family. He could trace his ancestries all the way back to Andronicus. And he wanted to do something different in his life, and he wanted to become a great scientist, so he went to work with Landau, and he took up this experiment and did it. And what he measured was that the normal fluid density at low temperature scaled as temperature to the fourth power. Now, they may not be obvious to you that that's an interesting result, but we can show that it's quite different from what you would get with a Bose-Einstein condensate. So let's try for the BEC result. Let's see if we can calculate this. A non-interacting BEC. The normal fluid density is the total density minus the superfluid density, and we can calculate that by just integrating over all modes in the sample by h bar cubed, except for p equals 0. P equals 0 is the p not equal to 0. P equals 0 is the condensed mode, where the macroscopic fraction has formed, But all other modes are occupied by the Bose occupation factor. Beta is the temperature. Beta equals 1 over kBt. And epsilon p here is just the excitation spectrum, p squared over 2m, and nb of x is the usual 1 over e to the x minus 1. So we can do this integral very swiftly. How do we do it? To calculate this integral, put myself down in this corner. To calculate this integral, we define q is beta to the 1/2 times p. So then this integral here, let me scroll this up. Okay, so this integral here, way up here, then comes down here and becomes, we just have to count factors of p. We get t to the 3/2 times the integral d3q over 2 pi h bar cubed, and 1 over e to the q squared over 2m minus 1. And this integral here just gives us, just gives us some number, and so the end result, is that the normal fluid fraction goes as just t to the 3/2. Okay, very different from what Andronikashvili actually measured. And of course, Landau knew very well that Andronikashvili was not going to measure t to the 3/2. He knew he was going to measure t to the 4th. So how did Landau know this? What was Landau's calculation? So Landau's calculation, very similar to the calculation he did for the critical velocity. We want to think about the situation in two different reference frames. So we're going to have a wall like this, stationary, and in one frame, the lab frame, the superfluid is going to be moving along, but there will be a normal fluid which is at rest. V normal will be sitting equals 0, because the normal fluid interacts with the wall and eventually comes to rest. At 0 temperature, we expect it's going to be all superfluid and there won't be any normal fluid. So we'll assume we're at some finite temperature. We can also think about being in another reference frame. So in the other reference frame, the wall is moving. The wall is moving this way, like this. And the wall will be at the same velocity as the normal fluid. Normal fluid like this, like that. Normal fluid. B normal is moving at the same velocity as the wall, and the superfluid is at rest. Okay, and if I want to know what the density is, the density of the normal fluid, all I need to do is figure out in this situation here how much fluid is flowing, because superfluid isn't flowing in this reference frame. In this reference frame over here, the superfluid isn't flowing, and so if I can calculate the total current density in this frame, I will know the so in superfluid rest frame, rest frame, the normal fluid current is just the normal fluid density times the normal fluid velocity. And so this is the thing I want to calculate by figuring out what the total normal fluid current is. Okay. So as before, we have an energy spectrum of excitations that we can make in the superfluid rest frame. In the superfluid rest frame, there's a excitation spectrum that looks like this. This is in super rest frame. And in the lab frame, the excitation spectrum is EP minus V dot P. Okay. And as before, what we had before earlier, when we were actually considering, when we were calculating the critical velocity, we were calculating something where we were sort of assuming that it was all superfluid. We were considering a critical velocity for a superfluid at say 0 temperature, and we found that if we argued that if this spectrum is ever negative, then you get dissipation. However, even if it's positive, you can still excite these excitations if you're at finite temperature. So these excitations can be excited thermally, and with a let's move myself up there. Can be excited thermally with a probability of the Bose factor n Bose of E of p minus v dot p, like that. Okay. So if I've created excitations thermally by populating them with the Bose factor, the total current density is going to be just integrate over all possible momenta, 2 pi h bar cubed in the usual way. Then how much momentum does each one have? If I'm calculating the total mass current density, I want to integrate the momentum of all the particles, add it up, and times this Bose factor of beta E of p minus v dot p. Okay. Now let's just assume the velocity is small for a second, because we can do our experiment here with big velocity or small velocity. So let's just use a small velocity and expand for small v. Expand small v. Okay, so we can write the mass current density here, J. I'd say it's a subscript n because it's the normal mass current density, but in fact it's the entire mass current density because the superfluid part is at rest. But I'm giving it a subscript to remind us that this is the normal part where we're integrating, where we're calculating. So we'll just write this as integral d3p over 2 pi h bar cubed as usual. The first term will be p times Bose factor beta E of p, like that. And then the subleading term will be p, that's the p out, that's this guy here. And then expanding this Bose factor will give me a beta v dot p here, and then Bose factor prime of beta E of p. Okay, so I just took a derivative Taylor series in this factor here. Okay, now this integral here, the integral of the first term, is zero by symmetry, that all directions are equivalent here, and if we're integrating a vector, we're going to get 0. So the only part that's interesting is this part here. Okay, so we're left then with this integral, and let's just make our life simple. Assume that the velocity is in the x direction. So we can then have that the normal fluid current density is then pulling out this. Oops, come back there. Pulling out this this vx here. We'll then have a factor of vx. We'll have a factor of beta from up here. We get beta. We have integral d3p over 2 pi h bar cubed, and we have what's left. Okay, there's a px here. It was a vx, so it has to be a px, and then there's a p here as well. Okay, now so there's a p vector here. That's the p vector out front, and there's a px sitting here as well. And then what's left over is minus nb prime of beta E of p. you can do one more thing. Realize that the only so this p vector has has an x direction, a y direction, and a z direction. But the only one that's is going to be non-zero once I do this integral over all three directions of space is the px direction. The py direction and the pz direction are going to give me 0 again by symmetry. Only the px direction squared is going to give me something non-zero. Okay, so I can rewrite it mvx beta integral d3p over 2 pi h bar cubed px squared, and then this minus nv prime beta e of p, like that. Okay. All right. So this is the result, and the this factor here is then the normal fluid density, because if you go all the way back up to here, remember that the normal fluid density is the proportionality factor between the mass current density and the velocity. So we're trying to calculate this big factor here. So let's actually try to do it. Case 1 easy case is a non-interacting BEC. We already calculated what the normal fluid density was in a BEC when it's t to the 3/2, but let's just check to make sure we get the same result. So again, we will set Q equals beta to the 1/2 times P, and then we'll scale out J. Well, okay, so the factor we're looking at here, rho n, is it has a beta out front, and then we scale out how many factors of P. So there's 3 factors of P here and 2 factors of P here, giving us a net factor of beta to the minus 5/2, 5 factors, and then an integral d3q over 2 pi h bar cubed qx squared n Bose prime with a minus sign of q squared over 2m. This long integral here is just some number. This thing is a number, and the end result, rho n, is t to the minus to the plus 3/2, which is exactly what we calculated previously for the number density for a non-interacting BEC. In fact, with a little bit of work, you can actually calculate this number here and show that it is in fact exactly the same as this number here, where we calculated before for the normal fluid density, as well it should be. Okay, now let's do the more interesting case, case 2. An interacting BEC or superfluid. Now, this case, the important thing to realize is that E of P is going to be proportional to P plus ... because we have a sound wave. And when we have a sound wave, the physics of a sound wave is that any time the particles interact with each other, if you compress, you can transfer pressure via particles bumping into each other via the interaction, and that gives you a sound wave. And this is a calculation that we previously did. Well, where was it? Way back here. We mentioned that if you expand this spectrum here, E of P for small p, this is going to be proportional to P times some sound velocity. Also, for the weakly interacting Bose gas, we mentioned that before, and we'll calculate it again later. Okay, so let's try to calculate the normal fluid density for an interacting Bose gas. Let's again use this expression here. Copy, and let's just copy this and paste it here. Paste, and the superfluid density that we're interested in is this object here. And to calculate when there's a linear spectrum, we make a different substitution. We take Q is beta times p. And if we plug that in, we then have beta. Again, we have 5 powers of p in this expression here. And so that then gives us beta to the minus 5, and then times integral d3q over 2 pi h bar cubed, and then qx squared, and minus nb prime of c absolute q. And so again, this integral here is just some number, and we're left with rho n is t to the 4th, in agreement with Andronikashvili. So this scores a big victory for Landau and his way of thinking about superfluids by going to the superfluid rest frame and then transforming back into the lab frame. So that's where we end this lecture, and we will pick up next time by discussing charged superfluids, by which we mean superconductors, and seeing how far we can get just by thinking in terms of superfluid physics, but now adding a charge to the superfluid as well. So I'll see you next time, or I won't see you. Well, you'll see me, but I won't see you. Okay, good.